Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over a problem in which you have to figure out what the new equilibrium concentrations are when adding a certain amount of one of the species or compounds. So let's get into this. Okay, so here's the problem. The equilibrium constant Kc for the decomposition of COBr2 is 0.190 at 73 degrees Celsius. A mixture at equilibrium in a 2-liter flask, 2.00 liter flask, contains 0.295 molar CO, carbon monoxide, 0.295 molar Br2, and 0.455 molar COBr2. If 1.00 moles of CO is added to the system, what is the concentration in each compound after equilibrium is reestablished? Okay, so and then they gave us the equation right here. Oops, went the wrong way. So we have this equation here, COBr2 gas is in equilibrium with CO gas and Br2 gas. And so we need to figure out what the new equilibrium concentrations are going to be for each of these after adding 1 mole of CO to the mix. Okay, so the first thing we want to do is find out how many moles of CO we already have. And they gave us the concentration, so we have the concentration of CO right here, and we have the the liters, the volume of the flask right here. So we have the volume of the flask. And so we can use that to find out the number of moles. So here we're going to take the 2 liters of the flask here. So I have 2.00 liters over 1. I can use the molarity as a conversion factor since we know that molarity is moles over liters. So I have 0.295 molar CO. So that means I have 0.295 moles per liter. So then I have liters on the top here. I'm going to cancel them out. I'm going to put 1 liter on the bottom, and I'll have 0.295 molar, or moles, sorry. Moles of the CO. And so liters are going to cancel out. So to find the moles, I multiply those together. And when I do that, I get 0.590 moles of CO. All right, so now that this is what I have in equilibrium right now, right? But we're going to add 1.00 moles more. So now I'm going to add that to this. So I have 0.590 moles of CO. I'm going to add to it another mole, 1.00 moles of CO. And of course, that's going to be equal to 1.590 moles of CO. So now I have the new number of moles. So this is the total number of moles I have now. But now I have to find what the concentration is after adding the 1 mole, right? So here, I know, again, go back to the 2 liters volume. So now I'm going to have to take the moles, the new amount of moles, 1.590 moles of CO. I'm going to divide that by 2.00 liters. And when I divide that, I get, what do I get? 0.795. So 0.795 molar of CO. So now I have the concentration of CO after that I have added 1 mole of CO to the mixture. Now the mixture before I added the 1 mole of CO was already at equilibrium, and when I added the 1 mole of CO, I have now disrupted equilibrium, and now equilibrium needs to be established. So the concentrations I have are no longer equilibrium concentrations. So let's go ahead and set up our ice table. So here I have the new molarity of CO. So let's go ahead and set up our ice table. So I'm going to set it up here. So ice, 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 baby. Okay, so yes, that was a throwback 80s. If you know what the reference, good job. If you don't worry about it. Okay, so we have CO, our new concentration is going to be here, so we have 0.795 molar. And the other concentrations are going to be the same as before, so but no longer at equilibrium. So those are no longer equilibrium concentrations because we've changed the concentration of CO. So Br2 is still 0.295 molar to start with. And then for the COBr2, that is still 0.455. So we'll put that 0.455 molar. Okay. And so those are the equilibrium, or those are the initial concentrations to start with. And so now I can do my ice table. So how do I know which way this is going to shift? Well, one thing you could do is you could find the quotient Q, the reaction quotient Q, and then compare that to the K value. They gave us a K value of 0.190, so you could do it that way. But a simpler way of doing it would be to just figure out and use Le Chatelier's principle. So Le Chatelier's principle says that if you disturb the equilibrium of a system, it's going to shift in order to undo that change, right? So if I add something, then it's going to shift in the direction to get rid of it or use it up. If I take something away, it's going to shift in the direction to make more of it. In this case, we added more CO to the reaction mixture. So since I added product, it's now going to use this up and make more reactants. So basically it's going to shift towards the reactants to take away, use up some of the CO in order to make more COBr2. So we can now figure out what the change is and identify and describe that in terms of X. So I'm going to, since it's shifting towards the reactants, I'm going to add an X amount here, right? And again, since it's shifting towards reactants, I'm going to lose product. So I'm going to lose an X amount here, and I'm going to lose an X amount here. Notice that the stoichiometry is the ratio 1 to 1 to 1, so your X's are also 1 to 1 to 1. We're gaining X here, we're losing X amount here because of this shift this way. And so now I just add these together. So this is going to be 0.455 plus X. This is going to be 0.795 minus X. And this is going to be 0.295 minus X. Okay, so now I am ready to set up my equilibrium constant expression. So here we have Kc is equal to products over reactants. So here I'm going to have the concentration of CO multiplied by the concentration of BR2. And remember, these are raised to the power of the coefficients. So the coefficients are 1, so the powers here are 1s. We don't write the 1s, but they're understood to be there. Okay, so now I put the reactant, so it's going to be the concentration of COBr2, and again, raised to the power of 1. And so here I have my equilibrium expression, my equilibrium constant expression, and so now I can plug in the equilibrium concentrations in terms of x, okay? Oh, and let's go ahead and put this in. So we have products over reactants, so we're going to have 0.795 minus x multiplied by BR2 concentration, which is that one here. So that's going to be 0.295 minus x, and then divided by the concentration of COBr2, which is this right here. So we're going to divide by 0.455 plus x. And remember, Kc, all this is equal to Kc, which is 0.190. So we'll put that here, 0.190. Okay, so let me just double check here. All right, so here, now that I have this set up, the question is, can I use the x is small approximation? Is the x here going to be so small as to be negligible and therefore ignored in the calculation here? Well, there's a couple of problems here. One, if x was small, we would be able to eliminate x from each of these, and x would be gone, and so that would be strange, right? So that indicates probably we're not going to be able to do that. Also, notice that the K value here is 0.190, close to 1. And look at the concentrations that we have to begin with. They're all 0.29, 0.79, 0.45. Those are really close to the K value. So since the K value, the equilibrium constant, is really close to the same, how should I say, same level as your initial concentrations, then this indicates quite clearly that the x is small approximation will not work. Typically, in order to identify whether or not the x is small approximation will work, you need the K value to be much, much smaller than the starting initial concentrations, right? By at least a magnitude of a factor of 100, maybe even 1,000 minimum, right? But these are on the same level, right? 0.29, 0.3 is very close to 0.19 or 0.2. So they're too close together. So we can't use the x is small approximation here. So we're going to have to, do the quadratic formula. So we have to manipulate this and create a quadratic equation from this. So what we're going to have to do is first multiply both sides by this on the bottom, right? So if I multiply on this side here, 0.455 minus or plus x, right? If I'm multiplying here, then I multiply over here, so this is going to be 0.455 minus, or plus x, sorry, plus x. All right, so then this cancels out here, and so I end up with 0.795 minus x multiplied by 0.295 minus x, and that's going to be equal to 0.190 times 0.455 plus x. All right, so I've simplified this. Now the next step is to distribute this to each of these. So multiply 0.190 times this, and then multiply it by x. This you'll have to do the FOIL method, unfoil it. So this will be multiplied to this, and then your negative x will be multiplied to this, and you'll get 4 terms that can then be added together. So let's go ahead and do that a little bit here. Okay, so then when I do that, I get 0. Let's see, 0.0. Where is it? 8645 plus 0.190x. And then I get 0.23. So on this side, I'm going to get 0.234525. So 4525. And then minus 109x. So minus 1.09x. And then I get plus x squared, so plus x squared. Okay, so then I have this, and now I just get, since I have x squared plus term x plus this without an x here, this term here, now I can add the x's on this side, so, and then bring this over, so I get everything all the way onto one side equal to 0. And when I do that, I get, do I have space? Yes. So I'll get 0 is equal to 0.148, 0.148, 0.75 minus 1.28 minus 1.280x plus x squared. Okay, so now that I have my quadratic equation, I can plug everything now into the quadratic formula. So let's go ahead and do that. Okay, so here I have my quadratic formula. I left the quadratic equation down here. So what you have to remember is that the coefficients in front of your x squared, x, and no x right here, this here, is going to be A, B, or C according to this here. So the coefficient here is A, the coefficient here is B, and this is C. And so since it's not written here, the coefficient in front of the x squared is a 1. So when we plug A, B, and C, we have B, B, A, C, and A. So we're going to plug these values into the quadratic formula. So x is going to be equal to negative B, which is already negative. So it's going to be negative multiplied by negative 1.280. So 1.280, right? And then it's going to be plus or minus the square root of b squared. Again, b is this negative number here, so negative 1.280 squared minus 4 times a. A is 1. Let's put the 1 there. That's 1. So it's going to be 4 times 1 times c. This is c. Right, so 0.148075. Probably don't need to put in all of those digits. 3 or 4 is probably fine, but you know, I'm anal. And then we're going to divide this by 2A. So then A again is 1. And now all we have to do is multiply, divide, add, subtract, right? So here, once you got that, then you're going to end up with, let's see, 1.1 5139, or, so x is equal to 1.15139, wait, hold on a second, 1.15139, or 1287. 1287. All right, so those are the two x values that we get from the quadratic formula. So which one is the correct one? Well, if we go back to the equilibrium concentration expressions, if you remember that the equilibrium concentration here was, let me write it here, so the equilibrium concentration of COBr2 was equal to, what was that equal to? 0.455 plus x. We don't need this anymore, so let me get the space. And then we add the CO, that equilibrium concentration was 0.795. So the concentration of CO, this is at equilibrium, is equal to 0.795 minus x. And then the concentration of Br2 at equilibrium was 0.295 minus x. And so right away, hopefully you can see which one is going to make most sense. So if I'm subtracting x, if x is equal to 1.15139, and I subtract that from 0.795 or 0.295, I get a negative value for concentration, which is absurd, right? We shouldn't get negative concentrations. What does that even mean, right? So that indicates that this here, this value is not the correct value, so we're going to have to go with that one. So now we can plug in this for x. So then this becomes 0.455 plus x, or plus 0.1287. And then we add those together, we get, what do we get? 0.584. 0.584. We're going to round to 3 sig figs here. And that's concentration for COBr2, the new equilibrium concentration. And then we do the same thing for CO. That's going to be 0.795 minus x, which is 0.1287. And then we get, for that one, 0.666. So 0.666 molar for CO. And then Br2, that's going to be 0.295 minus 0.1287. And that's going to be 0.166. 0.166 molar. And this is the new concentration of the species at equilibrium after adding 1 mole of CO to the mixture. And so that, ladies and gentlemen, is how you answer and work out this sort of problem. I hope this was helpful. If you learned anything, if you found this interesting and helped you in any way, then please by all means like the video, share the video, hit that like button over there. Also, do me a solid, subscribe to my channel, help me out. When you do, please click the notification bell. When you do that, click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me and have a great day.